Alright, in this video I'm just going to demonstrate how you could write a simple Riemann sum integration function using arrays. I did this in a previous tutorial using a for loop, and I'm just going to show you how you could write the same function but do it with arrays in a much shorter, compact syntax. So this was the function that I wrote that took the approximated the integral of some function that we pass in f between the bounds of a and b. So these are integration bounds, and n is the number of rectangles that we would use to approximate this this function using our Riemann sum. So it looks something like this. This is some function, and we approximate the area underneath this curve, which is the integral of this function, by taking and adding up a whole bunch of boxes that have height heights equal to the function values and the width of delta x, some finite width. So the integral of x squared can be approximated, or y squared, where y is equal to x squared, as this Riemann sum of the function value times dx. So sum running from 1 to n, where n, this would be the first box, second box, third box, all the way up to the nth box. Okay, so how can we do that using arrays instead? Well, all I'm going to do is I'm going to create a new function here, and I'm going to title it integrate f. I'm going to call it f array, and can I give it the same input arguments as we did for that other one? So a function, integration bounds, and a number of rectangles, and I'm going to have it output an approximation for the integral, which I'm going to name that variable int. So first thing is I need to have a rectangle width, just like I did in the last one. So I'm going to define that to be dx is equal to b minus a, all divided by n. Divided by n. Alright, and you'll notice always in my functions I always put the semicolon after a command. That makes it so that this command, the output of this command is suppressed when I run it. That's useful when you're defining functions. Typically when you write a function, when you call a function, you want to call it, give it some input, and then have it return the output. And you don't want to see all its intermediate calculations, what it does. So that's why we put semicolons there. Just a reminder to my students and anybody else who watches these videos. Okay, so I've got my box width determined by my bounds and the number of boxes that I'm going to pass in. Now I'm just going to create an array, and I'm going to use the syntax that I introduced in the last video about arrays, where I have a starting point, and I want to actually, just like I'm showing in this little diagram here, I'm going to use the function values are going to be the function values at the right hand side of these rectangles. So there's I could use points here at the left hand side or at the midpoint, but I'm going to use the one at the right hand side. So that means my very first function point needs to be a plus delta x. So I want my array to start out at the point a plus dx, and I want it to go in steps of dx all the way to b. Now if I save this and then run it, I need to give a function here. Oh, I've got so I have this function called define. It's just squaring the function, and it's using this dot operator just so that you can pass an array into it, and it'll do the element-wise multiplication, or the element-wise power. So if I was just to define that, the way I would define it is function equals at the arguments z dot squared. Alright, so that's how that's defined, and you can see it up here, it's defined. Now I forgot to clear some other stuff here. So type in clear a comma b comma x comma I. There, get rid of those. Well, I guess it only works. Clear a, clear b, clear x, clear I. There we go. Clear answer 2. There we go. Alright, so if I run this now, run this function, integrate f array, integrate f array, and I pass it in my function. Let's go from 0 to 4, and let's do 2 boxes, 2 rectangles. Now we see my x values are going to be 2 and 4, which if this was my function, and let's say this was 4 right here, and we were only going to this point right here, then we'd have this value would be 2 and this value would be 4, and then this value right here would be 4 and this would be 16. Anyways, I hope that makes sense. So that's what this command is doing. It got printed out because I didn't put a semicolon on. As soon as I put a semicolon here and save it, now I run this and it's not going to output this x value. I could output it, I could run it as many times as I want, and it's not going to show me what those values are. So now what I want to do is I want to evaluate this my function that's getting passed in as f at these x values to get the heights of the boxes. So I'm going to define that array to be equal to, I'm going to call it fi, set it equal to f at x. And this will be the heights of all the rectangles. So if I run it now we see that fi gets set equal to 4 and 16, which is x, those x values squared. So the x values were 2 and 4, and so fi gets set equal to the square of those because we pass in x into this function, which the function we pass in is func, which is defined as z dot squared, and so those values get squared. So, but the fact is fi is an array. It has 2 components. Alright, now I can come up here and I could say define a new array called ai, and that's going to be equal to dx times fi, and this is going to be the areas of all the rectangles. So I can save that and run it just so you can see the output there. So these are the area of each rectangle, 2 times 4 and then 2 times 16. Those are the areas. And so the integral, the approximation for the integral is just going to be equal to the sum of all those areas. MATLAB has a nice sum function. You pass an array, one-dimensional array, and it'll return the sum. So now I can do this, save it. I think I did save it, yep. And run it. And it returns the approximation for the integral. Now, The actual value for the integral of x squared between 0 and 4 is just going to be x cubed divided by 3, evaluated the bounds a and b, which are 0 and 4, which comes out to be 64 thirds. So that's the true value of the integral. We see with two rectangles we get a value of 40, which is very bad, but we can rapidly increase this, use 200 rectangles, and we see that our approximation to the integral gets a lot better. And now we've written the same function that we did here, but we didn't have to use a for loop. We used arrays instead. And so it's very nice, short, and compact. Alright, that's it for this video, and we'll see you in the next.